Everyone. So in today's class, I am going to discuss about the Grignard reagent. Grignard reagent. Grignard reagent is mostly represented by RMgX, where the magnesium and the halogen bond is ionic in nature, and the alkyl part and the magnesium bond is covalent in nature. That's why this requires del positive, this requires del negative. All right. So, and of course, this ionic bond. Now, Grignard reagent is a very famous organometallic compound, and it was invented by Victor Grignard. It was synthesis by Victor Grignard in the year 1900. And after 12 years, he got the Nobel Prize in chemistry for discovering this reagent. No other scientist has got this much credit because it's a very important compound. From Grignard reagent, we can synthesize all kinds of organic compounds, almost all kinds of organic compounds, right? So let us see. This is one of the organometallic compound. It is one of the organometallic compound. Now, what is organometallic compound? First of all, organometallic compounds are those compounds in which the carbon forms bond with metal. For example, here metal can be lithium, or metal can be magnesium, metal can be sodium or potassium, metal can be zinc, cadmium, even lead, mercury, copper, etc. Some of the very famous organometallics we already know that, like dialkyl zinc, that is known as Franklin reagent, or we can also have dialkyl cadmium, or we can also have dialkyl lithium cuprate. It is used in core house synthesis, right, for the synthesis of alkane. And then very famous C2H5 4PB tetrahydride anti-knocking agent. Now we are not using because lead is poisonous. So these are the famous organometallic compounds. We already know about them. Okay, Franklin reagent, dialkyl cadmium. This is lithium cuprate. Core house synthesis for the synthesis of symmetrical as well as unsymmetrical alkane. So these are the reagents, also known as Gilman's reagent. This one is known as Gilman's reagent, Franklin reagent, Franklin reagent. Now, okay, we will going to discuss specifically about the Grignard reagent and why we are using only magnesium and halogens. Okay, here in place of X we can use over here chlorine or bromine. Okay, your iodine also. Okay, but fluorine is not used. Fluorine is not used. Okay, because that bond is very strong, so difficult to break that bond, and that is also doesn't show. Reactivity is poor. All right. Okay. So now my question is that why we are taking magnesium and why not others? Let us discuss about this organometallic nature. Suppose I have taken carbon in the form sodium. Now carbon in the form of magnesium, sodium, magnesium, lithium, zinc, cadmium, lead. Let me write this one. Now, generally what happens if we are having carbon and sodium? Now you know that sodium reactivity, sodium and carbon, this bond will be ionic in nature. This bond will be ionic in nature, and we know that if you are using sodium, Woods reaction will take place. So it will not behave as a good organometallic compound because this bond will be ionic in nature, right? Now, let us talk about the RMgX or RLI. Now, they both can form organometallic compound, but the thing is that lithium size is very small, and here the polarization will be more. According to Fazan's rule, polarization will be more because the lithium cation size is very small. So more is the polarization and more is the covalent character. So here the covalent character will be more, and we want maximum polarization between carbon and the metal. That is the meaning of organometallic compound. That their electronegativity should be more, polarization should be more, and it should show more polarization. That is why the reactivity will be more. So here the covalent nature is comparatively less as compared to. So that is why this is a good organometallic compound as compared to lithium. Here this bond is more polarization because the size is small according to Fazan's rule, and this is also more covalent nature. Here this is less covalent, more ionic character is there, okay, as compared to this one. So this is regarded as a better organometallic compound. Other than that, zinc and cadmium, their reactivity is further decreases, so they are less reactive organometallic compounds as compared to the zinc. So this will form a proper organometallic compound. This will form an ionic compound and highly reactive. So definitely that will not work in case of organometallic compound. Okay. So let us now discuss about the Grignard reagent preparation. Preparation of Grignard reagent. Preparation. So now we can prepare preparation of Grignard reagent RMGX. Okay, we can prepare from alkyl halide. So here RX is there, in alkyl halide is there. I can take here chlorine, bromine, iodine, and I will treat this with magnesium and dry ether. So from here I will be getting RMGX. In short, I will need to tell you the mechanism because magnesium has 2 electrons. So here between carbon and the halogen, the polarization will be there. This will have del negative, this will have del positive. Now what will happen? One of the electrons, now due to the polarization, this electron will shift towards the halogen and one of the electrons will be shifted towards the carbon part. So from here we will be getting R dot X minus and Mg plus, okay, Mg plus and the dot. Now they will form, now this free radical, they will form a bond. That means after this stage we will have RMgX, where this bond is del positive, del negative, and this is ionic bond. This is ionic in nature. Okay. So in place of R, that is means in place of alkyl, you can take aryl also. Okay, aryl halide. That means you can take here. Okay, for example, if I have to take aryl halide, all right, let me write this also, aryl halide. Okay, and here I have got magnesium as well as dry ether. Now the same thing will happen. A free radical mechanism will happen, and we will be getting this kind of Grignard reagent, that is MgX. Okay, this is not the nucleophile. You don't consider this one as the double bond character like this, and because double bond character, so this bond will, this magnesium we will insert. Okay, this is not a substitution reaction, but rather a radical mechanism is there. So that is why they can form this. So for example, I have got C2H5Cl and I am going to treat with magnesium and dry ether. So definitely the compound will be C2H5MgCl or Grignard reagent, in which magnesium will acquire del positive and carbon will acquire, alkyl part will acquire del negative, and of course magnesium and chlorine bond is ionic in nature. So this is the preparation of Grignard reagent from magnesium and dry ether. We can also use THF, tetrahydrofuran. Okay, so now I will discuss why we are using dry ether and tetrahydrofuran. So now I will going to discuss the use of dry ether or tetrahydrofuran. So as I have told you that suppose I have got any, so let us say I have got over here CS3 alkyl halide in the form of, okay, let me take this alkyl halide. Here I have got CS3Cl and I treat this with magnesium in the presence of dry ether, then I will be getting over here CS3MgBr, that is Grignard reagent. In place of magnesium, suppose I use this one CS3Cl in presence of sodium and dry ether, then you know that this is a Woods reaction and we will be getting ethane over here. Alright, or if you can use this one in place of, see, you can use any vinyl also, allyl also, even cyclic, again also cyclic, okay, like this way. Okay, suppose I have got this reaction, okay, suppose I have got this reaction, and if you treat with magnesium and dry ether, as I told you, you can also use tetrahydrofuran. This is your tetrahydrofuran, okay, THF. Okay, so if you will, these both are which kind of solvent? These are polar aprotic solvent. They do not furnish H+. So these are polar aprotic solvent. When you dry ether, then we will get this compound. Again, a Grignard reagent. So this way, this reaction works. Now I will going to discuss the function of dry ether. What is the use of dry ether or tetrahydrofuran? Basically, most of the time we are using dry ether. Okay, dry ether as a solvent. Okay, because let me discuss that part also. So generally, the ether which we are using here is diethyl ether. The ethers which we are using over here is diethyl ether. After the formation of Grignard reagent also, or before the formation also, that is very, very important. So basically, this is our ether, diethyl ether, C2H5O, okay, and here is our RMgX. Now magnesium has got +2 charge, let us say +2 charge. So this charge will be stabilized by, okay, C2H5. Now this is called solvation. Now this process is called as solvation. Now due to solvation, what happens? This lone pair electrons will somewhat involved in they will attracted toward this one. Okay, and this process is called solvation, and they will stabilize the plus charge of magnesium, and in that way this compound will become stable. Okay, if Grignard reagent we are not using dry ether, if ether another purpose of using ether is that ether is a very heavy solvent and it will not allow oxygen to come in contact with Grignard reagent. If oxygen will come, then definitely this Grignard reagent, Grignard reagent, when reacts with oxygen, will form peroxide, which will further convert into alcohol. Alright, and also even water. If Grignard reagent will come in contact with water also, then acid will form. We will see this one. So that is why Grignard reagent is stabilized by diethyl ether. Now someone will also say that why we cannot use methyl ether. Okay, why we cannot use methyl? Why are you using diethyl ether? So here also we understood this one, that in case of methyl ether, okay, we want to polarize it more. Okay, because if the groups more alkyl groups will be there, then inductive effect will be more, and here the we want more charges over here. We want more charges over here. All right. So this alkyl part, heavier alkyl part, will produce more polarity on this oxygen, and that is why when more oxygen polarity will be there, definitely it will stabilize this plus charge, and in this way the solution will occur more effectively and Grignard reagent will become more stable, right? This is the use. And also oxygen and water, it is heavier than oxygen, and also it doesn't water is also not there, so that is where this compound will become more stable. Now, after the short description of organometallic compounds, I told you organometallic compounds are those compounds in which more polarity should be there, more covalent nature should be there, and then I also told you the method of preparation of the organometallic compounds, especially the Grignard reagent. Okay, even RMGX and RLI, that means both Grignard reagent, as I told you already earlier, that RMGX and RLI, because here the covalent nature will be more because of the more polarization, so covalent nature will be more, but here the nature will be less covalent, that is more ionic nature will be there, this is more reactive, that is a better organometallic compound. And also we discuss the method of preparations, how we can prepare, and what will be the effect if we will using the sodium, and then what is the use of dry ether as a polar protic solvent. So these all things we have discussed. Now we will going to discuss the reactions shown by the Grignard reagent. Reactions shown by Grignard reagent. Now basically Grignard reagent means RMGX. Always we represent by del negative and del positive between the magnesium and the halogen, and of course here also the ionic bond is there, so del negative and del positive, but this is ionic in nature, more ionic in nature as compared to this one. So because it shows two types of reactions. This alkyl part can act as a base and can also act as a nucleophile. It can also act as a base and can also act as a nucleophile. Now what is base? Base is a substance which can accept H+. If it will accept H+, then it is acting as a base. For example, I am having one example. Let us say I have got CH3 minus, NH2 minus and OH minus. You see over here, in this case, all belong to the same period. And as you know that negative charge on more electronegative atom is more stable, and negative charge on less electronegative atom is less stable. So here the reactivity of this, if you compare the reactivity, then this one is definitely more reactive and more unstable, and this one is more stable. And what is its conjugate? So suppose this is my base. So what is its conjugate acid? Its conjugate acid is methane. And this is the conjugate acid, and its base is a strong base. Because alkane is a weak conjugate acid, its base is a strong base. So this will act as a strong base. Alright. So as we have discussed that it is a strong base. Here I have already explained Grignard and alkyl part is a strong base, because its conjugate acid is a weak acid, so it's a strong base. Now it will show acid-base reaction. Okay, it will show acid-base reaction. Acid-base reaction, if it is base, it will behave as the acid-base reaction. Acid-base reaction. Now one more important thing, we know that acid-base reactions are faster reactions. The most fastest reaction is the acid-base reaction. Okay, acid-base reaction, I will come back to this. Now nucleophile. Suppose Grignard, this alkyl part, this one is, suppose this R minus is our nucleophile, then on on what species it will attack? Definitely it is showing it will react on our carbonyl compounds. It will react on our carbonyl compounds like aldehyde or ketone. Aldehyde or ketone. And in this case, it will show nucleophilic addition reaction. Nucleophilic addition reaction. Alright? Second part is that this can also react with carboxylic acid groups or acid derivatives. If acid derivatives are there, then it will show nucleophilic addition followed by elimination reaction. Nucleophilic addition followed by elimination reaction, and also it can react with alkyl halide, and then simple this time the reaction will be SN2. So in nucleophilic state, it can react with aldehydes or ketones or acid derivatives or alkyl halides to show the SN2 reaction. Now, first I will going to show the acid-base reaction of the Grignard reagent. Acid base reaction. Now you see here R MgX del positive, del negative, and let me write over here HZ. Now suppose if hydrogen is connected to more electronegative atom like oxygen, like nitrogen, like sulfur, like halogen, or we can also say that sp hybridized carbon. In all this situation, this hydrogen del positive, this hydrogen will react and it will form the alkane, and of course in this case we will have MgZX. So this is acid base reaction. Not only this, even active methylines are there, right? Active methylines. Okay, active methylines, this will furnish, because here the this hydrogen is acidic in nature. If it is H plus, because of the electron withdrawing groups, this oxygen are present over here. Okay, so this oxygen is present over here, and because of this, okay, electron withdrawing groups are there. So so here we have seen that the case of where hydrogen is connected to all these more electronegative atoms, even carbon, sp hybridized carbon, and active methylene. You know what is the concept over here of active methylene? That suppose here we have got CH2, right? Now if I will remove hydrogen H plus from here, that means CH minus double bond after the removal of H plus. Now this CH minus will be stabilized by electron withdrawing group. These oxygens are there and this negative charge will be stabilized, right? So this one is stable conjugate base. So because of this is also will furnish H plus, and this is very acidic in nature. It will show acidic nature. So this active methylene. Not only this, even this compound also, you know that this compound, okay, this kind of compounds, where if I will going to remove H plus, when I am going to remove H plus, so now this will show aromatic nature because of the 6 pi electron conjugation, and it will be stabilized. So these all are situations where acid base reactions will furnish. Okay, we will discuss one by one. All right. So as I have written over here, in this case, you see over here, all are the source of hydrogen. All are the source of hydrogen, del positive, del negative, and they will show acid-base reaction. And in all the case, the one common product will be the methane. After that, here we can see in the first case, this will form MgCl, and here OH will connect over here. Alright. In this case, again, you see over here, this kind, the common product is this one, and this one will be MgCl, OD, and likewise we can make all the products likewise once the acidic H plus is released, so it will form methane in all the case. Alright, in all the case it will form methane because all these are connected to more electronegative atom, oxygen, nitrogen. Okay, not this one also, we are having more also. Let us see that also. Suppose I have got this compound, as I told you. Suppose I have got aryl magnesium halide. If I take aryl magnesium chloride and if I treat with our active methylene, in this case, of course, this will furnish H plus, and this H plus will combine with our magnesium. Here this will acquire del positive and this will acquire del negative, this carbon, and definitely we will get benzene over here. And other than benzene, we will be getting over here, and that is double bond O. Now CH minus will be connected with MgCl. Okay, another compound. Suppose I have got over here. Let me write over here CH3 MgCl, and if I am going to treat with cyclopentadienyl, so we very well know that this will also furnish H plus. And we will get acid base reaction methane. At the same time, this will form this side product, that is MgCl, because this will acquire del positive and this side it will be del minus. So this is the side product. So by this way we have seen that acid base reactions are possible. Alright. Let me take one sp hybridized carbon also. Suppose I have got over here CH3 MgCl and I want to react with CH3 triple bond CH. Now because it is sp3, the electronegativity here is 3.25, so it will release H plus. This H plus will combine with this del minus, del positive. Again methane will form, and the side product will be CH3 C triple bond C minus del minus and then MgCl. Right. So right here, that is the CH3 C triple bond C, then MgCl, del positive and del minus. Okay, so this way acid base reactions are shown. Okay, we will discuss the nucleophilic reactions shown by the Grignard reagent. So Grignard reagent can also act as a nucleophile. Okay, so what kind of reactions it will show? Now, in which case it will show the nucleophilic reactions? First of all, whenever hydrogen is not there, and a hydrogen is not there, and electrophilic site is present. Electrophilic site is present. on substrate, then it will show the nucleophilic addition reaction. Okay, let us discuss where and on which kind of substrates it will show. So first of all, it will show reaction on aldehyde and ketone. This kind of reaction will be nucleophilic addition reaction. Nucleophilic addition reaction. After this one, the acid and derivatives, acid derivatives like ester, acid chloride, acid halide, okay, amide, okay, acid anhydride, all these acid derivatives, they will show nucleophilic addition followed by elimination. That means SNAE, we can say that SNAE, nucleophilic addition followed by elimination. And then finally, the reaction shown by the alkyl halides. Alkyl halides. Okay, RX. So this is SN2 reactions. Okay, so one by one I am going to discuss about this one. Alright, so these are the reactions shown. So one by one I am going to discuss these reactions. Reactions shown by aldehydes. I have got a simple methyl magnesium bromide and I am going to treat with a simple formaldehyde. Now because here oxygen carries del negative charge, so this is del positive, and of course from here our del negative, that means this part will act as a nucleophile and it will attack over here, and the product which we will be getting over here after this is your HCH and then O. Here is our alkyl part CH3, and further on negative acidic hydrolysis we can do this. Okay, so it will form alcohol, that is our CH3 CH2OH. 1 degree alcohol, primary alcohol, we can get it. In place of formaldehyde, let us take any other aldehyde like acetaldehyde. So in this case the same thing will happen, and this time we will be getting a 2 degree alcohol. Okay, a 2 degree alcohol will form. Let us it will be something like this: CH3 CHOH and CH3. The 2 degree alcohol will form. Okay, this is your 1 degree alcohol, this is your 2 degree alcohol. And if I take any ketone, CH3C, double bond O, CH3, and I treat this with Grignard reagent, then in this case I will be getting over here CH3, COH, CH3, and here also CH3, a 3 degree alcohol. Okay, so reaction shown by aldehydes and ketones. Simple aldehyde will give me 1 degree alcohol, then acetaldehyde will give me 2 degree alcohol. I can take any other aldehyde other than formaldehyde. All different types of aldehyde will give me 2 degree alcohol, and a ketone will give me 3 degree alcohol. Right. Now, after that we will going to discuss the acid derivatives. Acid derivatives. Reaction shown by acid derivatives. I will say take acid chloride. Let us say acid chloride. So generally the reaction shown here is SNAE, nucleophilic addition followed by elimination. So again I am taking this one, C2H5 MgCl, ethyl magnesium chloride, treating with CH3 C double bond O Cl. Now this part, here this part, here see here, this will attack over here. That means this is our del negative, this is our del positive, and this nucleophile will be here, it will attack, and this will be our leaving group Lg. This will be our leaving group, And finally, the product which we are getting over here is CH3. Then we are getting over here CO negative, and this is our C2H5, C2H5, and after that we can do the acidic hydrolysis. Okay, again we can do the acidic hydrolysis, and we will be getting over here the alcohol, that is the 2-degree alcohol, we can get it. Okay, so this is the reaction shown by any other acid derivatives. You can take acid halide, acid chloride, acid amide, ester also. So these are the products. There they will show SNAE. Now discuss the reaction shown by the alkyl halide. Reaction shown by the alkyl halides. Alkyl halides. Okay, so here is our CS3 MgBr reacting with, let us say, CS3Cl. So as you know that it is a very simple SN2 mechanism. This is our leaving group and this is our attacking site from here. So definitely here we will be getting, that is CH3, ethane is formed, and at the same time the byproduct will be MgCl and Br. So this is SN2 mechanism, simple SN2 reactions is shown. So now I'll wrap up this class, session here only, and here I have shown you the two types of reactions shown by the Grignard reagent. That is one of the acid-base reaction. Another one is the liquophilic reactions. Acid-base reactions are comparatively faster. Whenever we will be having any acidic hydrogen, okay, any acidic hydrogen, already discussed, any acidic hydrogen, either from this case also, okay, these all, okay, generally the fluorine is, this body is very strong, so this reactivity will be less as compared to, we can take also these. So these all are highly acidic reactions, so this is so acid-base reaction in case of this one, and here also we will be getting the methane as the major product. So this is all about the Grignard reagent. Some good questions I will take in the next class. Thank you very much.